Greetings to Dr. Arif. We are Group 3. Here we are going to present our lab report of Experiment 6, which is about bowl pressure gauge. Here's our team member. We have Lok Wei En, Muhammad Yuman, Chun Chun Fu, and also Toh Han Ting. The experiment is about calibration of a bowl pressure gauge. Calibration is a process of configuring an instrument to provide a result of a sample within an acceptable range. This process is important to ensure the result obtained from the measuring instrument is accurate. The result obtained from a sample will be compared with the theoretical result of the same sample. Bowl pressure gauge is a mechanical pressure measuring instrument. It can be used to measure the pressure of liquid or gaseous medium. As accuracy of the pressure gauge is depend on its calibration, the gauge must be calibrated from time to time, especially after applying to a high pressure. The objective of our experiment is calibrate a bowl pressure gauge using dead wax and confirm the accuracy level of the device on measuring gauge pressure. The scope of our experiment is to determine the maximum and minimum pressure reading of bowl pressure gauge and also to determine the percentage of error for bowl pressure gauge. Here's the simple theory of how the bowl pressure gauge works. First, we connect the gauge with a pipeline by socket block with section B. Once the gauge is connected with a pipeline, the inlet pipe with section A will let the pressure from medium flow in and cause the Bourdon tube with section D. The C-shape tube reflects when pressure is applied. A higher pressure will make it strengthen slightly. So the small movement will be converted into a large movement by a pivot and gear with section E and F, and cause the indicator needle with section G move across a scale to show the pressure level. When pressure goes up, the needle moves along the scale. When the pressure drops, the needle drops back. The working principle applied on the gauge is Pascal law. So the Pascal law states that the force applied onto an enclosed fluid is transmitted uniformly in all directions throughout the fluid regardless the shape of the container. Means that the force per unit area applied on section 1 is same as the force per unit area applied on section 2. So the same concept we can apply for our gauge. The reading we get from our gauge shall be the same as the pressure applied on the piston, and the theoretical pressure applied on the piston we can calculated by using the total weight we add on the piston, which is mg, divided by the cross-sectional area of the piston, which is PA.
My name is Muhammad and today I will be presenting about the experimental setup. So the apparatus and material we use is Bourdon tube pressure gauge, piston, and dead weight tester. And you can refer the figure show here. So next, for the methodology, preparation of apparatus. Begin by removing the piston and dead weight tester from the Bourdon tube pressure gauge setup, measuring and record the mass of each dead weight tester. Note and document the specification of the Bourdon tube pressure gauge, including the cross-sectional area of the piston and the mass of the piston itself. This information is recorded on the gauge platform for reference. And second one, filling the cylinder tube connected to the Bourdon tube pressure gauge with water or oil until it is completely full, ensuring there are no air gaps. Third one is inserting the piston and removing air bubbles. Carefully place the piston into the cylinder tube. Gently tap the apparatus to eliminate any trapped air bubbles, ensuring that the system is fully primed with water for accurate gauge pressure reading. Fourth, initial gauge pressure reading. Record the initial gauge pressure reading from the Bourdon tube pressure gauge before placing any weights on the piston. For step number 5, applying incremental mass. So, place a 0.5 kg dead weight tester on the piston platform and record the gauge pressure reading. Increase the mass on the piston incrementally by 0.5 kg, recording the gauge pressure at each increment until a maximum of 5 kg is reached. And number 6, removing the incremental mass. Begin with the maximum 5 kg weight and remove 0.5 kg increments from the piston platform, recording the gauge pressure reading at each decrement until all weights have been removed. And 7, system reset, which is remove the piston from the cylinder tube and drain the water from the apparatus to reset the system for the next measurement cycle. And last one is repetition for averaging. Repeat steps 1 through 7 2 additional time to obtain an average gauge pressure reading for each weight increment, enhancing the reliability of the data collected. So here the video example for the experiment.
Today everyone, my name is Dr. Lee and this is my assistant engineer, The experiment begins on putting the piston into the ring. When you put it, you want to ensure the power is still constant. Take down the reading, first reading. After that, put on the weight and take the reading. That's the first and second reading. After that, increase the weight. Third reading. And continue with all the weights.
The result of our experiment. The first table is the theoretical pressure and the second table is for the gauge pressure. And this is our proof or our result. Okay, for the first table, we have record the mass of dead weight tested added and the mass of piston, and hence we calculate the total mass. And we use the equation to calculate the theoretical pressure also from the total mass. Okay, and then for the table, we can know we use the dead weight tester added from 0 kilo to 5 kilogram. And the total mass will be from 1 kilo to 6 kilo. Okay, for the second table, this is the table of mass and gauge pressure. We record both the loading and unloading gauge pressure, and we repeat the experiment for 3 times, which is we record this one, including the dead weight tester for the total mass 1 kilo to 6 kilo, and then we unloading the dead weight until 0. This is one time of experiment. And we repeat the experiment 3 times in total to get the average.
And now we are going to discuss about the percentage error of our pressure gauge. The percentage error can be determined by using the absolute difference between theoretical value and experimental value divided by theoretical value times 100%. And this is our calculated result. So according to table 3, during the mass loading process, the higher percentage of relative error of gauge pressure value obtained is 27.83%, but the lowest percentage of relative error is 0.18%. When loading the mass, the highest percentage of relative error of gauge pressure value obtained is 10.36%, but the lowest percentage of relative error is 0.18%. The average percentage of relative error of gauge pressure obtained from mass loading process is 7.81%, but the average percentage relative error of gauge pressure obtained from mass unloading process is 3.39%. Generally, the percentage of relative error of gauge pressure value obtained when loading the dead weight tester is slightly higher than the percentage of relative error of gauge pressure value obtained when unloading the dead weight testers. This indicates that most of the experiment value of gauge pressure obtained from a mass unloading process are closer to the theoretical value of gauge pressure. This is shown at value of gauge pressure at total mass of 5.5 kg during mass unloading process, in which the percentage of relative error is only 0.81%.
So for discussion number 2 is source of error and method to minimize the error. In this experiment, one of the source of error that contribute to the inaccuracy of the data is the parallax error when taking the experimental value of gauge pressure from the scale reading of the Bourdon tube pressure gauge. This error can be minimized by ensuring the observer's eyes level always perpendicular to the scale reading of the Bourdon tube pressure gauge when taking the reading of the Bourdon pressure gauge value. Okay. Besides, the source of error that contribute to the inaccuracy of the data is the friction between the piston surface and the cylinder tube. The friction might cause the piston unable to move up or down when increasing or decreasing the mass of dead weight tester placed on the piston platform. This will contribute error to the experimental value of gauge pressure obtained. To minimize this error, the observer can gently rotate the piston before placing the dead weight tester on the piston platform and before removing the dead weight tester away from the piston platform.
To discuss about the third question, which is the repeatability and accuracy of this equipment. So the standard deviation of the collected data can be used to assess the equipment accuracy and repeatability. So the following formula are used to determine the standard deviation of the gauge pressure data received from the mass loading and unloading process. So standard deviation equal to value of the gauge pressure obtained minus the average value of the gauge pressure over number of data, then square root. So this is the table for which the value of the standard deviation for data obtained for the gauge pressure during the mass loading and unloading. So for mass loading, the standard deviation are 2, and the standard deviation for the mass unloading are 2.16. So the total mass are from 1 kilogram to 6 kilogram. So according to the table 4, the average value of the standard deviation obtained from process of loading is 2, and the standard deviation obtained from the mass unloading is 2.16. So both value of standard deviation is less than 2.5, which indicate that the equipment has a good repeatability for measuring the value for pressure for both different procedures. So the accuracy of the equipment can be determined by comparing the theoretical and experimental value of the gauge pressure obtained. So according to table 3, which is the percentage error. So this one is the table 3 percentage of relative error. Okay, so from table 3, the average percentage of relative error from the mass loading is 7.81%, whereas the average percentage of relative error for mass unloading is 3.39%. Since the average percentage of relative error of the gauge pressure obtained from loading procedure are more than 5, which is the 7.81, so the equipment is not accurate enough to measure the value of the gauge pressure. So in conclusion, we can say that the equipment used in experiment has a good repeatability but fair accuracy when measuring the gauge pressure value.
Conclusion, we conduct an experiment to calibrate a Bourdon field pressure gauge speed using that way. According to our result, the percentage error of relative error of gauge pressure obtained is relatively low, where there is a total mass from 3 to 5 kg on the piston platform during unloading the mass. Other than that, the percentage of relative error of gauge pressure is relatively high, which is shown in table 3. This indicates that the Bourdon field pressure gauge is not accurate to measure gauge pressure volume. According to table 3, the average percentage of relative error of gauge pressure obtained from the mass loading process is 7.81%, whereas the average percentage of relative error of gauge pressure obtained from mass unloading process is 3.39%. According to our result, most of the experiment volume of gauge pressure obtained from mass unloading process are closer to the theoretical volume of gauge pressure compared to the data obtained from mass loading process. One of the source of error for this experiment is parallel error. To minimize this error, the observer should always keep the ice level perpendicular to the scale reading of Bourdon tube pressure gauge. Other than the error is the friction between the piston surface and the cylinder tube. To minimize this error, the observer need to gently rotate the piston to ensure the piston is not stuck in the cylinder tube. The equipment used in this experiment have a good rapidity but has low accuracy when comparing the theoretical and experimental result of them. This is because the result obtained from both mass loading and unloading procedure using in this experiment have small volume of standard deviation. However, the average percentage of relative error of gauge pressure obtained from both mass loading procedure are more than 5%.
So for the safety procedure before the experiment, we should inspect the Bourdon pressure gauge and associated the equipment for wear, corrosion, or damage. We should wear a lab collar or the flame-resistant apron and avoid the loose clothing or dangling jewelry. Okay, so when we set up the procedure, we should mount the Bourdon pressure gauge securely in this holder, ensuring it's stable and properly aligned. The pressure gauge should be installed perpendicular to the horizontal. The measuring point of the pressure gauge and the instrument installation are in the same horizontal position, whether additional height error correction is considered. The distance between the pressure gauge installation and the measuring point should be as short as possible to avoid the slow indication. And we should also ensure the tightness, and there should not be the leakage, especially for flammable and explosive gas media and toxic and harmful media. Okay, so after when we finish the experiment, we should release pressure slowly and carefully, standing to the side of any valve to avoid exposure to any released material. We should also ensure the area is well ventilated during and after the depressurization process. And after the experiment, we should inspect the gauge and the system for any sign of wear or damage, and we should clean the work area thoroughly, depositing of any material. So the safety procedures that we found in reference are the 6. So this is the reference that we use in these experiments. Okay, so thank you, doctor.